All right, good evening, everyone. How's it going? Hey, Polina, you're here. All right, welcome. Hope I'm saying your name right. It's like Gus is here. Good to see you, Mr. Liu Dahl. Taking another shot at this. All right, appreciate that. Welcome, everyone. We are talking HSRP and ACLs tonight. Let's take a look at that agenda here. And, we are walking again through the CCNA ICND2 Blueprint, and we've got one section here that we're splitting into two separate nights. So QoS, quality of service, is such a big topic that I didn't see fit to cover HSRP and access lists and quality of service in the same night. It just didn't seem like that would give any of them enough attention. So, we're covering HSRP and access lists tonight, and we will cover QoS on the other side of the new year. So just a reminder to everybody as well that this is the last live session for a few weeks. We're going to take 2 weeks off. We have literally Tuesday nights, Christmas Eve, and New Year's Eve on the next 2 nights. So we're going to take those off. Hopefully everybody can get a little bit of a break from the studying because rest is important, breaks are important. All the science supports that, so make sure you enjoy the holiday season. I do remember, though, I will say this. I have a fun memory because I got my CCNA on January 2nd. So I didn't really follow my own advice. I definitely studied through the holidays. But I made sure to take a few of those days off, Christmas Day. It was largely, my cram session was between Christmas Day and New Year's Day. And so we didn't really do anything. We celebrated New Year's Eve, stayed up late or what have you. But New Year's Day was just hitting the books for me. And I went and I took it January 2nd, get this, 2006. That's how old I am. So it's been a little while. Okay, plan on taking ICND2 for Christmas. I hope not on Christmas Day, Polina, but hey, you know what? If your exam centers are open, then go for it. But yeah, hopefully that's a good Christmas present to wrap this up and get your CCNA. Very good. So our agenda tonight, what we have is, what I've got on the screen is what Cisco expects us to know about these two topics. Again, ICND2 is not expecting us to be experts at HSRP and to know every little dial and nerd knob that we can configure with it. Same with access lists, honestly. We don't have to have everything down pat. So as we cover these topics, we're going to do a lot of whiteboarding tonight. I do have some bad news. My lab crashed and burned on me when I tried to fire it up earlier this evening. And so my New Year's resolution is to come back with a much better lab because it's already caused me a lot of grief over the last few weeks. And just the tool that I'm using I don't think is very quality. So we're going to step up our lab game in 2020 for sure. So I apologize, but I don't have any configuration to show off tonight. However, we will talk about some syntax and as well just, hey, if you've got a router or a switch or anything that you have access to at home, then definitely follow along. So, all right, good. So I'm seeing some people already, plans to take ICND2 in January. Awesome. Yeah, quick reminder to everybody, February 23rd is our last day. So we have to get our CCNA by February 23rd. February 24th, the bad news is if we don't get it by then we're done. And we have to take the new CCNA. But the good news, and the reason we're all here, right, is because if we do pass it by February 23rd, we get the new CCNA. And that's just going to start all of us out on the right foot for being part of the new certification world that Cisco is building, because CCENT is going away, and this new CCNA is going to be really the new foundational, not just foundational, really they're building a lot on top of the CCNA. And so to have that in the new year, that's going to be a happy 2020. So y'all just keep working on it and be encouraged. So with HSRP, we're going to talk about priority, preemption, version. This is funny because I'm actually looking to the left, and I'm going to have to put the agenda over here so that when I look at the screen, it looks like I'm looking at it. Anyways, priority, preemption, and versioning. And with access lists, we'll cover exactly what they want: standard, extended, and names are named. So let's get right to it. So there we go. So let's talk about HSRP first. We will get to access lists. First of all, as always, what is the problem we're trying to solve? All of these technologies are great, but if it's a problem, or I should say, if it's a solution looking for a problem, it doesn't do any of us any good. Now, HSRP is such a big topic, and Cisco wants us to know it as much as anything, so we know that there has to be value. But let's talk about, first of all, what the value is around what we call these first hop redundancy protocols. And it's going to be a little bit of alphabet soup tonight, but we do need to understand some of these acronyms. So FHRP is what I just said, first hop redundancy protocol. FHRP really is the generic word for all of the different protocols that we can use to support what we call gateway redundancy. So the idea here is this: if we have a network with a bunch of hosts, or one host, it doesn't matter how many hosts we have, we tend to have what we call the default gateway. And that default gateway in my home is my router. In most of your homes, it's probably the router that you have. Maybe it's provided by your ISP, or maybe you went out and bought it yourself. At work, within the organizations, this could be a core switch, could be a router. Usually it's going to be, it has to be a layer 3 device of some kind, whether it's a router or a switch or what have you. And I will have, and let's say my IP address is, 192.168.100, and we'll just say .150 is my IP address. My neighbors is .151. And then we have a default gateway configured as well. And that default gateway is going to be the same on both of us. It's going to point us to where our next hop goes. So if this router is .1, we would both have .1 configured as our default gateway. So what this means is if I know where I'm going, and for most PCs, the only way that I can know where I'm going is if I'm going somewhere on the same subnet. So I'm talking to my neighbor, for example. If I were going to send a packet or send a file or something to my neighbor at .151, that traffic's never going to hit the router. It's just going to go out here across the LAN because, again, CCNA concept, I would ARP for that IP address. I would get the MAC address and I could communicate directly via layer 2. Hopefully that makes sense. However, most of what our computers do is not talking to other neighbors on our subnets. The best example of that might be a printer, or again, if you truly are sharing files between, like sending a file directly, but there's not a lot of applications for that these days that don't involve a server or something out on the internet. And the internet, of course, is the ultimate destination for a lot of traffic. We're trying to get out towards the internet, or again, maybe my data center. This is where all of my servers and my applications might live within my organization. And so we have to be careful of, just understanding this whole concept, right? The default gateway, as we can tell, is very, very important because it gets us out to the internet. All right, so you can tell where we're going with this, especially those of you who have studied this before, but I just said this thing is really, really important. We've got this tremendously important device, and how many do we have? One in the picture. So if this guy goes down, I have no access to any other resources, and that's not good. That's not very good. So what are we going to do? Well, we're going to be smart. We're going to say, hey, let's deploy a second one of these devices, whatever it is. In our case, let's just say that this is a router. And so we're going to deploy a second router, and we'll give this a .2 address because it can't have .1 because that would be a duplicate IP address. But we still have a problem because my default gateway right here is one IP address. It's .1. Now, let's go back to that failure scenario. If this were to fail, and by the way, I guess I have to make another assumption, which is that the second router has access to these upstream devices as well. Better not be a bridge to nowhere. So now, in my scenario, .1 goes down. Am I live? I've got this path out to the internet, but my problem is I'm still trying to send all of my traffic to .1, and .1 is dead in the water. So because .1 is dead, I didn't actually gain much here. What I did gain was I could go to every single PC in my network and say, hey, your default gateway is now .2. Your default gateway is now .2. And go to all of those devices, which, again, describing a bad scenario here. We don't want to do this, okay? This is not a solution. We can't go around and reconfigure every single device to get back out when there's a failure. Especially, that thing might have rebooted. It might be coming back up. We might have a new one coming in, and maybe that one truly fried, and we called up Cisco TAC, and Cisco's sending us a new one. It's gonna be here in 2 hours. Okay, well, we're just gonna be down for 2 hours. I'm not gonna go reconfigure my whole network. We want something, and it's all silly anyways, because this router is sitting there waiting for traffic. So the idea here is that we are going to use this concept of, I'll leave that one up, of a first hop redundancy protocol. That first hop redundancy protocol is going to enable me to very quickly move from the router that failed here and get going on this secondary router. Hopefully that all is clear. We're going to go into the details of how this happens. So good and bad news about this, right? Bad news, there are a lot of FHRPs, really 3 if you want. 3 is a lot. But there are a number of FHRPs that we need to know if in our day-to-day being good network engineers. The good news is Cisco only wants us to know one of those, so we don't have to freak out and study a bunch of topics. Okay, so we have 3 different protocols that are first hop redundancy protocol. First hop redundancy protocols, FHRPs. So we have HSRP, which was, by the way, this was created by Cisco. We've talked a few times, right? What happens? Cisco invents something really cool. The industry says, hey, we want that too. And usually Cisco helps with that too. It's not like, there's no animosity there. But, HSRP stands for the hot spare redundant router protocol. All right, what's HSRP stand for, somebody? You'd think I would have looked that up beforehand. Hot standby routing protocol. I got it. Hot standby routing protocol. And that S is actually significant because our syntax is based on standby. Then we have the VRRP, Virtual Routing Redundancy Protocol, I believe. And then the Global Load Balancing Protocol, GLBP. All right, so by the way, this was also invented by Cisco. Now, of these 3, which one do you think Cisco wants us to learn? Probably one of the 2 Cisco ones, and they do. We already know this because we're talking about HSRP tonight. So we need to know HSRP. One of the reasons for that is that if you're a Cisco network, the world has not moved away from HSRP. Remember we talked about we had ISL trunking instead of .1Q trunking, and the world has moved away from .1Q trunking, or I'm sorry, no, we've moved away from ISL, which was Cisco, and we've moved towards .1Q. That hasn't happened really with VRRP and HSRP, and there's a couple of reasons for that, but the primary reason is that Cisco continues to enhance HSRP and give us some really neat features, especially in the data center side of things. They do some really cool stuff with HSRP. So it's very relevant for us to learn HSRP, probably even more relevant to learn HSRP than VRRP, even though this is a standards-based protocol. Now, outside of a Cisco network, you're going to see only VRRP because that's the only one that is a standards-based. All right, hot standby. Thanks for confirming that, Mr. Ludall. All right, Mr. Let's call you Mr. So, all right. Hey, Jimmy, thanks for swinging by. Hopefully your internet gets repaired. So go fix it. Use HSRP. I don't think that's probably the problem. Okay, so we've got these 3 protocols. Again, HSRP is what we're going to want to study. Either way, again, the goal for all 3 of these protocols is to very quickly enable our network to swing over to the second router. And believe it or not, they actually, all 3 of them do it in slightly different ways. So we're going to talk and focus on HSRP. I'll call attention to VRRP and GLBP because, again, that makes us a more well-rounded network engineer. But, again, for CCNA, we don't want to delve too deep into the other protocols. We want to focus on HSRP. So let's get us a new whiteboard and dive into that. Okay. So the way HSRP is going to work is, again, we've got our 2 routers, and those are sitting on one layer 2 domain. Which, by the way, means what? If they're on the same layer 2 domain, they have to have the same something. What is that? Hopefully, we're thinking subnets, right? Like, again, I mentioned earlier, just a random IP subnet, 192.168, maybe .1.0/24. Okay, so that subnet mask is indicating that all of the devices on this within this layer 2 domain are on this, are going to start with 192.168.1. Okay. Is there a protocol number to HSRP? That's a great question. I don't think so. Well, actually, there must be because it's not running across TCP or UDP. So that's a good question. We'll look that up. So if indeed all of them are on the same subnet, then we're going to see that they again have those same. They're on the same subnet. Let's just put it that way. So again, we used this example earlier. I was .150, and we had a .1. My gateway is equal to .1. That doesn't change with an HSRP environment. Whether I have a single router and he's .1, or I have two routers, either way, that part doesn't change. What does change, and this is the important part about HSRP, what does change is who owns this .1. Who is this? Because in a single router environment, that is my physical upstream router. Here at my house, I don't have two routers. I'd love to say that I do for whatever reason, because I'm not too worried about that thing going down. And if it does go down, I mean, I can drive to Walmart or Best Buy and buy another one and be back up and running. My kids won't get to watch Netflix, so that's too bad. Hey, Jake, thanks for chiming in there. So, okay, we are using UDP. Cool. I did not know that. So I tell you what, you learn a lot when you're training because of the good questions. So by the way, please continue to throw those good questions out there. So we're using UDP. So it wouldn't have a specific IP protocol number. If you were going to write an access list to block HSRP, we'd be looking at blocking that UDP port number. Okay, so who owns that .1? Again, I don't have two here. That's my physical router. But when we do have two, with HSRP, we're going to say neither of them own it. Okay, what that means is that neither of them have .1 assigned to them. So we're going to have to assign two different IP addresses. Let's say .2 and .3. And they're going to share this .1 as what we call a virtual IP address, or a VIP. .1. I told you it was going to be alphabet soup tonight. lots of TLAs, right? Three-letter acronyms, TLAs. Yeah, I love that one. So .1 is going to be a virtual IP address that's shared between the two. So what's that mean? What's a virtual IP address? What that means is that when I ARP, because again, how do I find out who to send it to? Send a packet to. I do an ARP. So I'm going to ARP for .1, and somebody's going to respond to that. And the one who's going to respond to that is what we call the HSRP primary. So we have an HSRP primary, which basically means it's the router in charge of this. And let's say that the router on the left is in charge. Okay, so that router, will send the ARP response. That router is going to send the ARP response, and that router, this is important too, is going to say, we think about what an ARP is. An ARP is saying, hey, who has this IP address, and what's the response? What comes back? Think about that for a moment. What's coming back in response to my ARP request? What's coming back is a MAC address. Now, that MAC address usually is my physical MAC address. So I've got an interface, I've got a physical MAC address. I'm going to tell you, hey, this is me. But with HSRP, we're not going to send a physical MAC address. We're going to send a virtual MAC address, or a VMAC. And that virtual MAC address is also shared between the two routers. Now, the HSRP is going to be busy, the HSRP primary is going to be busy, because as more and more clients are ARPing for that and sending traffic, that HSRP primary is going to be doing all of the responding, saying, okay, yep, it's me. Here you go. Send your traffic to me. But what's interesting about this is what happens if this router goes down. Did we lose the virtual IP address? Kind of, because the router that was answering that .1 went down, but it's virtual, so we didn't lose the virtual MAC address. Same with the virtual IP address. Yeah, whatever. Virtual MAC address. We didn't lose these things. This secondary router is going to be able to, technically, by the way, let's use real terms. This is the standby router. Okay, it's not the secondary, it's the standby. So the standby router is capable now of immediately, once it detects it, immediately starting to respond to those ARP requests. So all of a sudden, this router is responding to .1, and that MAC address, by the way, that virtual MAC address did not change. So since we're using the same IP address, same MAC address, the only thing that really needs to update is this layer 2 switch environment. But the router is going to send a gratuitous ARP and take care of that. That's a little beyond CCNA, maybe. I don't know where gratuitous ARPs and such fall into play, but I mean, we do, at least as CCNAs, we should be understanding that switches learn where MAC addresses are. And so if a switch learned that virtual MAC address lives out this interface, well, it's going to have to learn that it's out that interface. But taking that aside, let's stay in the world of layer 3 here. Within the world of layer 3, I just kept .1 active using this protocol, which means I don't have to reconfigure my devices. They still have .1 as their default gateway. In fact, the clients who have already ARPed and they already know the gateway's MAC address, they're even covered because, again, that VMAC persists. And so now, instead of sending traffic this way, I'm sending traffic to the other router. And guess what? My laptop doesn't know the difference. It wasn't touched in this. Okay, maybe I dropped a couple of packets while it was switching over, but hey, if it's an invisible process to the end clients, then we all win. Okay, so this is the concept of first hop redundancy protocols in general, but especially HSRP. All right. Any questions on any of this? Please don't hesitate to toss something into the chat, and we'll address that. Okay, this drawing got a little busy, so we're going to recreate it. So let's get this drawing back. We're going to see this drawing a lot, I tell you what. 2 routers connected to a single LAN device, or a LAN segment rather, with a device here. So this is my .150. Now we know this is .2, .3, .1 is shared between the two because we are running HSRP. Okay, so the next step in all of this is how do these routers decide who's the primary? Because that's a pretty important role. And also, how does the standby know when the primary goes down? All right, so what we're going to have here is we're going to have communications going across this LAN segment, because the first step, of course, is that they have to discover one another. All right, we start off, we have actually 3 states that we can be in. We need to talk about all of these. We have primary, we have standby, and then we have listening, which if you've studied spanning tree, listening can be bad because it means there's no network traffic happening, but it's a different situation. A listening router simply means it's not set to take over. The primary is the only active router that's responding, like we talked about, to all those messages. The standby is ready to jump in if needed, and the listenings are kind of just there. So that would be if we had 3, 4, or 5 different routers. But we do all start off in the listening state. So we're listening, we're sending these messages to each other, and we're comparing what we call the priority. The priority is a configured value, and these are some things we might need to know for the CCNA, because CCNA specifically calls out we need to understand priority. First of all, the default value is 100, and so, hey, there might be a tie right away. If we didn't change the configuration, we have a tie. So, first of all, let's talk about, if there's not a tie, highest wins. Okay, we want to configure the router, a router that we want to be the primary. If we have a router, we care. If we care, right? Maybe we don't care. But if we do care, usually it's best practice to be deterministic about these things, which means you know what's going to happen in a failure scenario. The highest IP address, the highest priority is going to win. We talked earlier during the spanning tree session, for those who are here, that as a general rule, this is not without exception, okay? There's rules and there are exceptions. There's always exceptions. But the general rule is that if you have a layer 3 protocol, the higher number wins. And if you have a layer 2 protocol, the lower number wins. So when we're talking about OSPF priority, that's a layer 3 protocol. The higher OSPF priority wins. When we talk about spanning tree protocol, well, that's a layer 2 protocol. The lower one wins. Well, what about multicast? Multicast PIM, that's a layer 3 concept. The higher IP address wins. IGMP, the layer 2 version of multicast. Guess what? The lower IP address wins. So, again, this is not a beats-all rule. In fact, I think, I don't know. We were just talking about something. Maybe it was, you know what I was thinking of? Administrative distance is a good rule breaker. Because you'd think that administrative distance is layer 3. We talked about routing a couple weeks ago. Administrative distance, the lower one wins. So there's going to be exceptions to this rule. But I will say that this, as a general rule of thumb, can help us kind of remember in a if nothing else, if you're taking an exam and you have to guess, then go with that rule. So the highest priority wins, and then ties are broken by IP address. So in our scenario here, we have a .2 and a .3, and they're talking to each other. If they're both configured with the same priority, the .3 would win the tiebreaker and become the primary router. All right, Polina has a thought here. When I tried this in the lab to trace route to the internet, I did not see the HSRP configured IP address. It showed the IP address of the active router. It says normal behavior on the Cisco FAQ. Correct, it would be normal behavior. Would it be the same for the MAC addresses? Okay, so you can't really get MAC addresses on the trace route. The only thing, trying to think of how this would actually function. So anytime, this is actually kind of an interesting thought, and it relates to HSRP. It's a good thought, Polina. The IP addresses from HSRP, anytime, let's say I'm on this router and I'm going to ping that client. Okay, anytime the router is going to send traffic, it's going to use the physical IP address as the source. Okay, it will never use the virtual IP. There we go. It will never use the virtual IP address as a source when it's sending traffic. Now, a trace route is effectively a ping, because what's happening is we're sending ICMP messages and setting the TTLs, and we're getting messages back and such. So it's sending an ICMP response as part of the trace route, and will always use the physical IP address. Now, from a MAC address perspective, if we were to look on this computer and we were to look at its ARP table, because, hey, even Windows, Linux machines, they all have ARP tables. We can look at that. We just need to make sure we have the right command. Pull up a command prompt. Isn't it ARP-A on Windows, I think? So when we're looking at the ARP table, it will have .1 and it will have the virtual MAC address. So we see the virtual MAC address manifested at times, because, as far as that PC is concerned, it doesn't know any better. But of course, it also happens to know the virtual IP address, because that's the gateway address that we gave it. So hopefully that answered your question. If it didn't, definitely chime back in and let me know. I want to be clear on that. But again, that is a great point, that Cisco, you'll never see this .1 if you're running trace routes, if you're running like Wireshark, if you're sniffing traffic. The only time you're going to see that IP address is when we're sending an ARP message. And technically, could we SSH to this? If I wanted to, could I SSH in here? Absolutely. Absolutely I could. Because when I target .1, I'm going to do that ARP. I'm going to get the virtual MAC address. I'm going to send out to .1. I'm going to be able to attach to that. So who's going to answer, though? Which one am I connecting to? It'll always be the primary. So anytime I want to connect to the HSRP address, I will connect to the primary router. If that primary router were to change, then the router I connect to is going to change. It's going to be different every time, potentially. So keep that in mind as well. All right. One of these days I'm going to learn to use layers like they're meant to be used in this program, so I can quickly get rid of all the purple or what have you. So we'll clean this up in a moment here, but I do want to finish out with this. So again, here's the key points that we need to know and understand for the CCNA. If we're going to take the ICND2, in all likelihood, they're going to ask or give a scenario, right, where you have two routers with different IP addresses and different priorities, and they're going to expect you to understand this process. All right, Pauline, I see. Yep, I was wondering if the ARP table would show the MAC address. All right, perfect. Yep. because that's its reality. This is as far as the PC is concerned, that's the reality of that. So any ARP table entries should have virtual IP address to virtual MAC address mapped. Yeah. Interestingly, I said I'd point out a couple of differences with VRRP and GLBP. One of the differences with VRRP is it doesn't use this virtual IP address concept. What it does is it more or less enables, let's say this is the backup, right? I think that is actually what it's called in VRRP. It's not called standby. I believe it's called the backup router. The backup would be able to use .2 if the primary router were to go down. So it's more like they all share the primary router's IP address, and so technically we use less IP addresses with VRRP. HSRP requires 3 IP addresses. It doesn't sound like much, but that's because we're talking about large subnets. Imagine when we have to do HSRP with like a /29. And /29 is 8 IP addresses minus 2 for the subnet and network IDs, and so now we're down to 6 IP addresses, and 3 of them just went to the routers. So in some situations, HSRP can rob us compared to VRRP of that extra IP address. Okay. I think that covers most of what I wanted to say here. I want to be clear on these two, the states. So we are going to have a primary router. Let's say that I've got this configured for a priority of 120. And let's say this one over here, this is no longer backup. That's a VRRP word. So this is the standby router. Let's say it has a priority of 100. We kept it at the default. And hey, let's just for fun say we've got a third router in here, and its priority is 90. Okay. This router will be, can you see that? You can't see that. All right, we'll just scratch that out. All right, so this router right here, let's say it has a priority of 90. That's good, right? All right. And the it will be in the listening state. Okay, it's going to be a listener. All right. So the ties go to IP and HSRP would be layer 3 protocols the highest. Yes, correct. The highest IP address would win a tiebreaker. Why would that be a tie? 2 routers. Oh, sorry. First of all, it's a priority check. We're comparing priorities first. Sorry for the confusion. We only compare IP addresses in the event of a tie. So over here, highest priority wins. Okay. The very first thing we're going to compare is priority. 120, for example, versus 100. Router on the left is going to win in that situation. The whole theory of using the IP address as the tiebreaker is going to be, or is because in theory we don't have duplicate IP addresses. So all right, good, that made sense. Okay, all right. So next topic. And draw our drawing again. All right, so let's say we've got now HSRP is .1 still, .2, .3, .150, gateway is .1. All right, so now we need to explore a new concept here, and this is called preemption. And this is a topic, again, that Cisco wants us to know for the CCNA. Preemption, let's consider this scenario. It's not true in every situation, but let's say both of these routers, in fact, let's not even make it a different router. Let's just make it the internet. Both of these routers, let's say, has a connection to the internet, each one. And we've got 2 connections here. Now, with HSRP, we can't use both of these. All of our traffic is going to go out one router. Now, we can load balance this across VLANs, and we should. We'll talk about that here in a little bit. But at the same time, for the most part, I'm going to use one router over the other. So if I'm in charge of the finances for an organization and we say, hey, you know what, we need 100 meg circuit for our organization, am I going to go out and buy a second 100 meg circuit for that link, even though we're going to use it maybe once every year or 2, ideally? Hopefully that router stays online more often than that. We're not going to use it very much. And so maybe I'll get a 10 meg backup circuit. So let's say we go through this whole process, right? Okay, this, by the way, is a fairly common situation. We've got a worse upstream path out the standby. So we've got primary, we've got standby, life is good, and of course, disaster strikes. This router goes down. Now, these two routers, by the way, are communicating with each other with keep alive messages. And we can change those, by the way. We can set the timers to be faster or whatever. We've got some control over that. But either way, they're sending each other messages. And so, hey, are you there? No. Hey, are you there? No. You know, after 3 attempts, or after so much time really technically has passed of sending keep alives, the standby router is going to say, hey, I guess I'm it. And it will become primary, which is what we want. And ideally, that happens within seconds, which we can configure HSRP to be maybe like a 1 second keep alive with a 3 second timeout. So within a few seconds, we're back up and running. Everything is good. And then, wouldn't you know it? Well, actually, no, this is a good thing. This router comes back online. So now our old primary comes back online. Now, one thing I probably should have mentioned in the last slide, but either way is fine, is that an election does not happen when a primary is already in place. Okay? So what that means is if we fire 2 routers up and they're both in that listening state, they're going to do the priority conversation. But that doesn't last too long. So assuming everything goes well, doesn't really matter. Either way, in this scenario, we've already got a primary. Our primary is up and running. Our second router came back, our primary router came back online, but because the primary is already established, we don't do another election. So this router is now the standby router. Clearly, this is not ideal because we're sitting on a 100 meg circuit compared to a 10 meg circuit, and I'd rather use the 100 meg circuit. And this guy is back up online here. We'll just kind of erase all that nasty looking red X. Okay, life is good. This router's back online. Other than some holes in it. I don't know. We drilled some holes in it to make it lighter. Can fix that, I guess. But either way, whoops, that didn't work at all. There we go. So either way, we see the problem here. Okay. Why does Cisco make it so that we don't immediately take over? Because we might have latency sensitive traffic going across here. Also, this router might go up and down and up and down. It might be rebooting, it might be cycling, we have no idea. Cisco wants us to be in control of when we redivert traffic to the original primary. And preemption is how we do this concept. Okay? The disaster. There's drill holes in the router when the router does not work. Yes, 100%. That'll work every time. You just gotta. It's just too heavy. Just drill some holes in it, make it lighter, and we're good. Gives it better airflow too. It's a nice side effect. Don't actually take my advice on that, at least in production. Okay. Either way, so we understand that there could be scenarios where we don't want to switch this back over to the original primary, and because of that, we I guess we have this concept of preemption, which the word preempt and the word preemption means I'm taking over, right? If I preempt something or preempt someone, I'm kind of getting in front of them. I'm taking over. Maybe I'm going to preemptively attack somebody in a video game before they attack me. I don't know. That's always the word that I use is preemptive strikes. It seems like because I'm playing games, I'm like, I'm going to get you before you get me. It's a preemptive strike. So preemption gets us out in front, which means we're going to take this router and get this router back out in front and make this router the primary again. Preemption is actually a there's syntax for this. What's the word I'm looking for? There's a command. There's an explicit command for preemption. Preemption is disabled by default. Okay? By default, preemption is disabled. This is an important concept. So when we're configuring HSRP, we need to use the command preempt if we want the router to take over for the other one. Now, we do not need preemption in the scenario we just described for the secondary to take over the standby. The standby will take over the primary without the preempt. Okay, it's only when I have a higher priority than the current primary, okay, which would happen in this scenario. If I have a higher priority than the other router, and I'm configured for preempt, it's a local configuration, and I'm configured for preempt, I will take over for that router. So we only need preempt on the primary router, technically. Could we put it on the secondary? Sure, there's no harm in that. I know I keep calling it secondary, it's the standby. Yeah, I mean, I lost my train of thought on that. So either way, oh yeah, could we configure it on the standby router? Yes, we could. So, what's this look like? Well, when we configure standby groups, we'll talk about. Give the syntax a moment here. I'll come back to the syntax. We'll do that on the next slide. So if I enable preempt on this router, when it comes back online, it's going to check its priority. Its priority, we believe we said it was 120. It's going to check the standby's priority. That's 100. And I'm going to preempt this router, and I'm going to take back over. So because I take back over functions, again, the virtual IP address and the virtual MAC address, they don't change through this whole process. Okay? So because they're not changing, this PC was sending to the left, then it was sending to the right, now it's going to send to the left again. It's oblivious to all of that. Okay, the switching, the layer 2 infrastructure is the one that's sending the destination MAC address to the appropriate port, so it's getting to the appropriate router. So because of that, the network takes care of all of this, and the PC doesn't have to worry about it. So now we have preempted the fact that we have a current primary. This router will go back to being standby, and we've already written it over here, but the router on the left will go from a listening state into the primary, or what would be the standby state into the primary state. Okay. Whew. Okay. So let's talk syntax a little bit. Okay. I want to make sure, double check the agenda real quick. Did we talk priority, preemption? Version. Yes, we'll come back to the version. Knew there was something. All right, but we do, of course, need to talk about syntax a little bit. And so HSRP, the concept of HSRP is that we can have multiple groups. Groups are how we enable multiple instances of HSRP within a single router. Would I need multiple instances of HSRP in a single router? Almost always yes. The reason for that is most routers, especially if it's a layer 3 switch, most routers and layer 3 devices are going to have a connectivity on one segment. Let's call this VLAN 10. And then, hey, guess what? They also have connectivity into VLAN 20. And we could keep doing this forever, right? And now we've also got connectivity into VLAN 30, 40, 50, 100, 1,000. Okay, so we can have as many VLANs as possible, but each VLAN, each connection here, each physical or sub interface, doesn't really matter. Each layer 3 interface, let's call it that. Each layer 3 interface needs its own instance of HSRP. This is where the groups come in. Okay, so we can run multiple groups on HSRP, and each interface is basically going to have its own group. Now, ideally, just from an organization perspective, we can we would want to make like group 10 be assigned to VLAN 10, whatever that layer 3 interface looks like. Okay, these layer 3 interfaces, if it's a layer 3 switch, would be a VLAN interface, a switched virtual interface, or an SVI. If it's a router, and we're doing what we call that concept of routing on a stick, where we have a trunk going up to the router and it's carrying all the VLANs, well, then we'd have sub-interfaces in that case, and those sub-interfaces would be where we'd assign these HSRP groups. So maybe we'd make group 10 be VLAN 10, 20 be VLAN 20, etc., etc. Ideally, that's the case. Now, does Cisco require us to do that? No. I could make group 10 be VLAN 20 and group 20 be VLAN 10. I would not advise that. This is for the human side of it, right? We want to organize ourselves logically. Mr. says, so there's only one primary, one standby at a time, so only a topology with 3 or more routers would be a router in the listening state. With the slight caveat that a router boots up into the listening state and then gets promoted up to one of the higher states. But yes, in a steady state environment, if you have 2 routers, you will not have any routers in the listening state from an HSRP perspective? Good question. All right. Incidentally, by the way, that concept of an HSRP single primary and standby, that's going to apply to each group individually. So I mentioned earlier, right, this concept of, well, what if I wanted to load balance these? Well, I can do that with HSRP groups. I could make, let me get the colors right. So VLAN 10, the router on the left could be the primary and the router on the right could be the standby, because maybe this is 120 and the standby is 100. But hey, for VLAN 20, it's a different group. I could do whatever I want. Maybe for VLAN 20, this is the secondary, the standby, because it's configured with a priority of 90. And the primary here on the right is configured for 100. This is a way that we can load balance traffic to the different upstream layer 3 gateways. And by the way, this is absolutely best practice. We would want to consider doing this in an environment, especially if we have many different subnets. We'd want to load balance them between the two as best we can, with the assumption that these upstream connections are the same. Okay, in the scenario where it's 100 meg on one side and 10 meg on the other, I mean, could we do a 10 to 1, throw one VLAN over to the right? Technically we could, but that might cause other problems. So when you're talking about an internet circuit, usually you're going to go with a single router. All right. Is there a max priority? Yes, I want to say it's 255. I think it's 0 to 255 is the priority range. So, and, okay, no, I was thinking of OSPF. I was going to say if the priority is 0, then that would be, you could disable, yeah, that I'm thinking of OSPF. And OSPF, if you give it a priority of 0, it'll never be a designated router on a segment. I was going to say the same thing for HSRP, but that's actually not true. Is this considered traffic shaping? Good question. It is not. So we'll talk about traffic shaping as part of QoS in the next, well, I guess in the new year, so it'll be in 3 weeks from tonight. Traffic shaping is a concept where, I'll give you the 10-second version. Let's say I've got one of these routers. I'm bringing in 100 meg and 100 megs of traffic and 100 megs of traffic downstream, and here's my internet circuit, and it's only 100 meg. What do I do with this? Traffic shaping is shaping this traffic to match 100 meg as much as possible, which literally means I'm going to keep information back and hope that I can kind of like get it out the door. Now, if I have 3 to 1 ratio there, I'm going to end up dropping traffic. But if I've got, let's say maybe it's 50 and 20 and 40, now that adds up to 110. That's too much. But if I hold some of that traffic back and release it afterwards, and I might be able to actually send that out at 100 meg and make sure all of the traffic gets through, that's called traffic shaping. Okay. So that's a QoS concept. So again, good question there. So that's shaping. We can ignore that as far as the HSRP conversation. Time-wise, okay, yeah, we're doing all right here. We're still about halfway done. Time to move on to access lists here in a few moments. All right, so I said we were going to do syntax, and we haven't done syntax yet. So you would think that the syntax for HSRP would involve the word HSRP, and it does not, with, again, the slight caveat being that it does on a Nexus switch. So I don't know how many people here are using Nexus switches within a data center. Nexus is my absolute favorite line of switches. I love Nexuses to death. Nexi to death? I don't know. It's an eternal debate. I love Nexus switches to death. And they actually use the word HSRP in the same way that they got away from some of Cisco's like Ether channels, now port channel and such. When Cisco designed HSRP within iOS, the big word we're going to want to watch for is standby. Okay. So what happens is I get onto an interface and I configure it with a group. So in my case, I might say standby 10. Then I get a sub prompt and I can configure all of these other concepts. I configure the priority value. I configure the IP address, by the way. I'd say IP and then I'd give it the address. And they don't say it's literally IP, not IP address, because IP address is used for assigning physical IP addresses. We don't want to confuse the two. So it'd be like IP in this case, the 192.168.1, I think it was .1, right? Yeah, .1.1. We can change the virtual MAC address, but we usually don't. And then so I didn't include like the priority. Let's say the priority is 120 or something along those lines. And then, can you see this? Oh, rats. Do that a lot. Okay. Well, we don't need to worry about the IP address. Yeah, let me just rewrite it. Sorry about that. Hang on. One of these days, I gotta mark off the area that I can't write in. Then I won't have that problem. Okay, so standby 10. Then we'd say priority as a subconfiguration of, again, maybe 120. And then we'd say the preempt, if we wanted to, that's a single command. And then, or single word command, I should say. And then the, what was the last thing? Priority, preemption. Yeah, the virtual IP address. So IP and then whatever the IP address is. That's the minimum of what we need for this. I did forget about version 2. So we need to, we could set the version number as well. I believe, unless I'm thinking of Nexus switches, that the version number happens. It's not a, it's on the interface, but I believe it's not under the group. I believe it's at the interface level. I'd have to double check that. But I understand that we can change the version. So let's talk about those versions, and then we'll move on to ACLs, because that is itself a pretty big topic. All right, so we're not going to spend a whole lot of time on this, but HSRP has 2 different versions, version 1, version 2. All right, version 1, and I'm not sure how much Cisco is going to want us to know about the difference between these two. Okay, there's a possibility that, I mean, because they don't clarify within the blueprint, we might need to know every little difference between these, or at least I would prepare for that. So there are some great articles online after this when you're like, okay, what did he say and what were all the things? Just go out and do a version 1 version versus version 2 search to make sure you know it all. However, for tonight's sake, the general differences between these two. First of all, they have I should say this. So the group number, remember we talked about groups? We support 256 groups in version 1. We support 4,096 groups in version 2. The idea here, of course, is that how many VLANs do we have? 4096, plus or minus the reserved ones. So we wanted the ability to assign groups based on VLANs. Remember what I just said about, hey, let's call group VLAN 10, let's call that group 10. Okay, well that worked well and good for version 1 until we hit, okay, here's VLAN 300, and the highest VLAN or highest group number I could give it was 256. So you did have some nasty, like, okay, yeah, group 10 is VLAN 10, but VLAN 300 is group 25 or what, you know what I mean? Like there were just problems with this. So Cisco wanted to enable the use of whatever VLAN you're mapping to, you can make the group number the same. Yeah, I play a lot of StarCraft, so Nexuses are awesome for chrono boosting. Yeah, it is. I haven't played StarCraft in 20 years, but it's been a long time. But I played the Zerg anyway, so I never really understood how the toss worked. All right, I think it's important to know the MAC addresses and maybe multicast. Yes, Polina, that is absolutely true. So, and you point out, so the next two things. The virtual IP address, oops, said that wrong. The multicast address, that's what I was going to say. Thank you. Okay, so the multicast address is different. Remember what I said, that these, when we had the two routers, that they were sending keep alives to each other? The way they were sending those keep alives are to a destination multicast address. The destination multicast address for version 1 is 224.0.0.2. This multicast address, I don't think multicast really shows up. I'd have to double check the blueprint how much multicast we have to know for CCNA. I believe it's none, but don't quote me on that. This .2 address is interesting because it actually doesn't belong to HSRP. They borrowed it. .2, the 224.0.0.2, is reserved for all routers on the subnet. So in the event, let's just make up a really weird scenario here. In the event that we have these two routers running HSRP, and for whatever reason, we have these three routers not running HSRP, but they're on the same subnet, they're going to get all of the keep alives in the same way that, we're sending it to each other. All three of the other routers, these guys down here, they're going to receive every single keep alive, even though they don't want to. They have to receive it, realize it's not for them, and drop it. Receive it, realize it's not for them, and drop it. And so with version 2, we changed it to be 224 0.0.0.102. Right. So now it's which is reserved for HSRP and GLBP. Technically uses the same one. But yeah, I would absolutely recommend that you know the difference. Number one in the groups, number two in the multicast. The virtual MAC address is the worst thing to learn. The virtual MAC address changes the format. In fact, I'm gonna have to pull up. Let me see here, because I do not have this memorized. I thought I had it pulled up. I have it here. Nope, I didn't write it down. All right, let's figure this out. What is the virtual MAC address range? Here it is. Okay, so we've got, well, here, we've got the version 2 at least here. So the version 2, where's my thing? There we go. The version 2 MAC address is a bunch of zeros, 0000 dot 0C9F dot F, and then the range. So let me make sure that y'all can see that. Okay, good. Whew, gotta squeeze it in there. When I say the range, what do I mean? Well, each group uses a different MAC address. So if I have group 0, this would be 000. If I have group 1, this would be 001. Because this is in hexadecimal, we've got 16 times 16 times 16, 2 to the 4 times 2 to the 4 times 2 to the 4 is 2 to the 12. 2 to the 12 is 4096. So, hey, guess what? That matches how many groups that we're able to have. So we can actually put, I mean, every single group will have its own unique virtual MAC address. I'm not seeing on a quick search, let me just say HSRP V1 VMAC, and we'll probably get it pretty fast. And well, I'm not seeing where that is. We definitely need to know the difference between them. So I'm not finding it real quick. If anybody finds it, then chime in. I apologize. I should have written that down in advance so I had that. But for whatever reason, it's not coming up in a quick search. I'm still looking, of course. Okay, is that it? That looks familiar. That looks like it's it. Use this range. Oh well. No, I guess that's not it. Oh, there it is. I think this is it. C07AC. That looks right to me. I remember, for whatever reason, I remember there being an AC. So, okay. So the MAC address on the version 1 side is still all zeros and then 0C, but then it defers to, it's got 07 and then dot, that's a 0, and then dot AC, and then a blank. All right, so we already see the fact that we don't have two numbers, or we only have 2 digits. Again, 16 in one, 16 in the other, 16 times 16 is 256. So in the same way that the MAC address changes per group in version 2, we have that same concept in version 1. Incidentally, if somebody could confirm that those MAC addresses are correct, if you happen to be out there looking as well, let me know, because I just want to make sure that I'm giving you good information. And again, I didn't have that one pulled up and ready. Okay, I think that's it. Let me check my notes. Okay, yep, that looks good. So that is it on HSRP. Any thoughts or questions? Chime in. We can come back and answer those. Otherwise, let's go on to access lists for our last 30 minutes. If I can get my whiteboard, there we go. All right, good old access lists. I will say access lists, I think, make people more nervous than it should. It's not that it's not a difficult concept. There are definitely nuances and little niche things that we have to understand about access lists. But overall, my best recommendation is just to practice using them. It's just like any math concept, right? When we learn a concept, you just got to sit down and do it. I'm a guy who honestly I don't spend a lot of time with access lists. I haven't for a long time, and so anytime I sit down to write an access list, it's like, oh man, and I go out and do a quick Google search to make sure I'm doing it right. But when you're doing it regularly, again, especially leading up to the CCNA, make sure that you are focusing in on labbing this, on entering access lists, testing them if you can to make sure you got everything right, etc. But generally speaking, it breaks down pretty well with to some fairly simple concepts that Cisco wants us to know. Speaking of which, let's go back here. So what does Cisco want us to know? Well, they're a little more vague with access lists than with HSRP. The HSRP is pretty clear. They want us to understand preemption. They want us to understand priority. They want us to understand version 1 versus version 2. That last one's probably the most vague, where, again, we don't necessarily know all of the things. But, we at least broke it down to the three main things. With access lists, they want us to understand standard and extended and named. Okay, well, assumedly what that means is we need to understand how to configure standard access lists and what the difference is between standard and extended and named also. We have to be able to configure those as well. And so it opens the door to a lot, and I understand that. But generally speaking, access lists tend to behave the same ways. So let's talk about that. Oh, hey, I've got some people chiming in. It's like Jake and Mr. saying, yes. Okay, good. Good. HSRP version 1 is 0C07.AC. Okay, good. That is what I wrote out. So if you were taking notes based on what I wrote, I believe we're accurate with that. Just pop that back up. So we had 0C9FF, good, which aligns to both of you. Okay, good. And 0C07, yeah, and then AC. Okay, good. So, yeah, so if you're taking notes, then you are good. If not, you can check the chat and get that information. So thank you to both of you very much for chiming in with that. Okay, so Cisco wants us to understand. Let's just talk about generally speaking again. Let's get back to I forgot I was showing the agenda. Sorry about that. All right, now we're looking at the whiteboard. All right, so let's just start talking about some of these access lists. All right, so generally speaking, I'm checking my notes, which is why I can't do two things at once. There are 4 things I wanted to say about access lists, about how they behave, regardless of the scenario. Okay, first of all, the biggest thing is this. We are looking for a match. Okay? I guess maybe I should back up a step and say access lists, the purpose of access lists, if we haven't looked at access lists yet, which, by the way, these were on IC&D 1, I believe, right? I mean, I definitely covered them in the IC&D 1 section, so I believe that it's in the IC&D 1. So I'm assuming everybody studying IC&D 2 has some experience with access lists at this point. But we understand that the purpose of an access list is to effectively be a little firewall. In fact, firewalls, back when they first were invented, that's all they were access lists. It's access control. It's looking at traffic coming in or going out and saying, can this traffic be allowed? So the concept, of course, is, are we going to permit it or are we going to deny it? Those are the 2 key words. Now, as we're going through an access list, there are a lot of different lines. Permit this traffic, deny that traffic, permit, deny, deny. And so the access list is going to be read sequentially. As traffic comes into an interface or goes out an interface with an access list applied, we're going to go through that access list and find the first match. Okay? If that first match is a permit statement, then it's permitted. If that first statement is a deny, it's going to be dropped. Now, what matters here is, what if my traffic matches a permit statement, but it also matches a deny statement? Well, because a router or network device, whatever we've got this access list on, because it's going sequentially, it's going to look at the first one, which assumedly is the order I wrote it. So the first line says permit, it's going to be permitted. I mean, we're not even going to check the other list. As soon as a match is found, boom, we're going to go with what that match says. Okay, so pay attention to that. It's the first. It's always the first match. All right, the next thing, we all love to talk about this. There is an implicit deny at the end of every access list. In other words, even if you don't explicitly state, if you do not configure, if the only line in your entire access list is permit this type of traffic, unless that says permit any, meaning it's going to just permit everything, the traffic will be compared to your line, permit some amount of traffic, and if it doesn't match that, the next line, even though you didn't configure it, is an implicit deny all. It's just going to drop whatever traffic doesn't match. So if we get to the end of the access list, it's just going to drop everything. So always keep that in mind. The third thing is that access lists, I already implied this, but they're always they're direction specific. They need to be applied in the inbound or outbound direction. Now you can apply the same access list inbound and outbound on the same interface. You can do that. But generally speaking, in production and in real life, to say that, access lists are usually designed to be one way, because the traffic going out is usually different than the traffic that you're trying to pay attention to coming back inside. Okay, so now keep in mind that an access list by default does not open up ports or open anything up coming in. So if you have everything coming in is denied, but you're allowing traffic outbound, well, the response traffic is going to get denied. So you have to be a little bit careful with that. There's things called reflexive access lists and other things that can open those ports for you, open up traffic. It's kind of like this concept that we have at home with NAT, right? Where traffic can't get into my router, but hey, if I send something out, the response traffic gets back. Okay, so we have to be careful with that with access lists. Keep in mind the directionality of our traffic and the directionality of these access lists. Okay, and the last thing, and this is, I think, what freaks the most people out, is simply that it uses wildcard masks. What are wildcard masks, and why do we use them? I wish I could tell you why, because I don't have a good answer for you. My guess is that Cisco wanted to be very intentional with where you were configuring them. Oh, you know what? I apologize. My mouth ran faster than my brain. Do you want to know what the difference is between a wildcard mask and a subnet mask? Can I tell you that? This is interesting because not many people know this. A subnet mask is a little bit of a diversion, but it's okay. The subnet mask is what? A set of ones, some amount of ones, followed by some amount of zeros. Okay. I didn't write exactly 32 ones and zeros on there, but a subnet mask would usually have, not usually, IPv4 subnet mask will always have 32 of these. Some number of ones, maybe 17, followed by 15 zeros. Okay. We like to, a pretty subnet mask is this, right? 255.255.0.0. This would be 8 ones, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 8 ones, right? Each one adds up to 255, and then 8 zeros. This is harder to cram in. 8 zeros and 8 zeros. So that would be a subnet mask. Okay. Now it's an inverse, right? A wildcard mask, usually the explanation for a wildcard mask is to say the inverse. And I've said this before. If you've been as part of our conversation here before, it's easy to say that. If I wanted the wildcard version of that subnet mask that I just wrote, it's going to be inverse. It's going to be 0.0.255.255. Within the world of subnet masks, what does a 1 mean? 1s mean we care about these. In the world of subnet masks, a 0 means I don't care about what that is, right? That's why, hey, with that subnet mask, as long as the first 2 octets all match, we care about those 2 octets. We're on the same subnet then. I don't care if your last digit is .1 or .2, right? I mean, they have to be different. At some point, an IP address has to be different. So wildcard mask, yes, we do change this. So now we've got 8 zeros, holy cow, trying to squeeze them in, and then 8 ones, and 8 ones. And it's backwards. It's the inverse. 0 with a wildcard mask means we care. Ones means that we don't. So I still haven't told you what the difference is between a subnet mask and a wild mask is fundamentally. Because if this was the only difference, we wouldn't use wildcard masks. We would not. We would just be like, okay, well, let's just enter the subnet mask then, because it's just the opposite. Okay? Wildcard masks. Can you read? Oh, rats. I got it under there. All right. So here it is. Here's the difference between wildcard mask and subnet mask. I'm just kind of like pausing for dramatic effect here. A subnet mask, remember what I said, it has to be a series of ones followed by a series of zeros. Saying the inverse for a wildcard mask is not true. To say a wildcard mask is a series of zeros followed by a series of ones is not true with wildcards. I could have a wildcard mask that does something crazy like this. 8 zeros, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1. You can't see it now. I'll take it to the next one. 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0. Okay? I could literally have a wildcard mask like that. It allows me to swap zeros and ones throughout the course of the wildcard mask. Very seldom do we do this. I would say never do we do this. Do we ever use wildcard masks? For the most part, no. In fact, Cisco got rid of wildcard masks on the Nexus for accessless configuration. The reason is we never use them. We never use what, they have a purpose. Their purpose is to avoid the rule of the subnet mask, which is to say it's all ones and then all zeros. But I could actually match all even IP addresses if I wanted to, right? Because I could make it so that, hey, if the last digit's a 0, which means it's even, that means that it doesn't end with 1, right? It's an even number. If it's 0, I could make it so that like multiples of 3 or multiples of 4 or what have you are allowed. Like I could do really weird things with multicast addresses. So that are with I don't know why I said multicast, with wildcard masks. There we go. Paulina, I read somewhere that wildcard masks were used before we had subnetting. When everyone was using class A, B, or C, and then later on people started subnetting. So now we have subnet masks and wildcard masks. I have no idea if that's true. I've never heard of that. But I do think that even if that is true, the fundamental difference is that we don't have to structure our wildcard masks like we do with subnet masks in the same way. So there you go. That's the great secret of wildcard masks and why Cisco put wildcard masks back to the original point. Like I said, my mouth ran faster than my brain on that one. I was saying, I don't know why Cisco used wildcard masks. Well, technically I do, but again, do we ever use it? No, we do not ever use it. You do not have to know that for the CCNA, by the way. You know why I know that is because at one point on the CCIE exam, when I was taking the CCIE, that was part of the, like, hey, you never know what Cisco's going to ask you on the CCIE. And if they tell you to allow these IP addresses with only one access list entry, or an ACE, what we call them, access control entry, then you need to understand how to do this with wildcard masks. And I was like, oh, wow, that's crazy. So what does Nexus use? Nexus uses subnet masks on their, in fact, they use slash notation on their access lists. So it's even, I mean, it's truly living the dream. It's like 192.168.1.100 or .0/24 or what have you. So we get away from wildcard masks within the Nexus world. Because again, we don't use them. Okay, so on to what Cisco actually wants us to know for the CCNA. Coming down to our last 15 minutes here. We talked about, actually, hold up. Let me check my notes because we've got, we were talking about standard, extended, and named. Okay, so what we've got here is, hold up real quick. Let me check one thing with my notes. There we go. Okay, we're good. So we have three different hello. What did I do? I deselected my brush somehow. There we go. Okay, we have three different types of access lists. We have standard, extended, and named. Okay, and named is technically, I mean, we're calling it a different type, but really we can have named standard lists and we can have named extended lists. So in the end, they follow named access lists are largely going to follow the same rules with a couple of exceptions. A standard access list, the biggest thing with a standard access list is we can only match the source IP. Okay? We cannot match the destination. So all I'm checking is when, hey, permit this traffic. It's looking at your source, can you talk out this interface, period, end of story. I couldn't with a standard access list say, hey, this is you're allowed to talk, but you're only allowed to talk out here, or maybe you're allowed to talk out, but you're not allowed to talk to this particular server, or what have you, right? That requires a destination, and in order to have a destination address consideration, we need to use an extended list. Destination IP. That's a weird N. There we go. Destination IP. Interestingly, when we're talking about named access lists, the other option really is what we call numbered. A numbered access list is kind of what we think of as the traditional standard and extended. What do I mean by numbered? Well, what I mean is the syntax is going to say, I'm going to call it, say, okay, access list. I'm configuring an access list. I say access-list, and then I give it a number, which doesn't seem that odd because, HSRP, we gave HSRP a group number, right? So this is like an access list number. Except the number is what defines whether it's a standard or extended list. And we absolutely have to learn this for CCNA. Okay? If I put, whatever number I put here is going to determine whether it's a standard list or whether it's an extended list. All right, so what are the numbers? Here, let me back this up because we're going to need that space. The numbers are, if it's a 1 through 99, that would be a standard list. If it's a number, 100 through 199, that's an extended list. Now, those are fairly easy to remember. What we need to make sure we memorize, and why I'm looking over here at my notes is because I don't have them memorized anymore. It's been so long. Is that Cisco realized that 100 is not really enough. Like, you might need more than 100 access lists on a router, or 99 in the case of standard. And so they gave more numbers. They gave us more numbers. Except they didn't, they'd already defined a lot of these number ranges, so they couldn't simply give us larger contiguous ranges. So the standard access list, unfortunately, it's way out there. It's 1300 to 1999, and then an extended list. That number is 2000 to 2699. Okay. Again, I apologize. I know I don't have them memorized, but you do. This is one of those do what I say, not what I do moments. You're going to absolutely want to have these memorized when you're going to take the IC&D too. So when we see that syntax, when we see access-list, and then a number, let's say it's 2112. I don't know. Access list 2112. And Cisco says on the exam, what type of access list is this? Is it a named access list? Is it standard? Is it extended? And then they'll have some throwaway in there like, I don't know, is it a taco access list or something like that? Like, no, it's not a taco access list. But because I've memorized this, I know 2112 fits into this range, and therefore it's an extended list. So these are the kinds of questions that we can probably expect on a Cisco exam. Incidentally, if they give you the full syntax, the fact that there's a destination IP address would be a good giveaway as well to pay attention to. Okay. So the other thing, there's one other thing that we get with extended access, technically two other things we get with extended access lists, and these are important, okay? We don't just get the destination IP address, we also get the ability to search for ports or compare for ports, as well as an IP number. IP versus, it gives you protocol, I'm just gonna call this protocol matching. Because really what it does is it allows you to match either by IP number, or by TCP, or by UDP, or by ICMP. Okay, these are our four main options for when we say we're permitting something. So an extended access list allows me to get so granular to say, Jeff, your machine can not talk to this IP address on this port. Okay, that's the level of granularity that we can get with extended access lists. With a standard access list, we can simply say, oh, you're Jeff, yes or no, based on the fact that it's my IP address. So there's not much that we can do with standard access lists, and by all rights, we're not really using them anymore. There are occasions where you'll use them, especially like if you just want to quickly make a log and compare. There are actually some log, if I remember right, some debug commands is what I'm thinking, not log, sorry. Some debug commands that have to reference a standard access list. There are one or two things out there that require a standard access list, but for the most part, we're going to stick with standard and extended. Okay, so named. The only thing with named access lists is that, number one, the syntax is different because we're not using a number anymore. And it's a little more different than just typing a name in instead of a number. We have to use the syntax IP access dash list instead of just access list. And then we have to give the name as well as whether it's an extended. So we'd say like test as the name. And then we would say whether it's extended or not. So we have to say extended or standard. So we're defining this. Using this syntax, it allows us to manipulate the lines. So using the other, there are two different syntax. We're going to talk about this on the next slide. We got about 9 minutes, so we'll be good. You have access dash list as a syntax type, and you have IP space access dash list. You can use either syntax for any of these. Okay, I could actually make an IP access list and then give it a number. 101 and make it extended or what have you. But technically that puts it into the named category, the named access list. It's just named 101. Not sure offhand as I question myself whether we can have a named access list and a numbered using the same number. We run that in the lab and test that and see what we have to say. If we use this second syntax type, we can edit an access list. One of the most notorious things about access lists is that you can't edit them. And so if you need to change it, what do people do? Have you seen this? I mean, I can't tell you how many times I've seen this, where we go out, we have to make a change in the access list. And so somebody goes out and we copy the whole thing, we paste it into a text file, we make the changes in the text file, we copy the whole thing, we go back to our command, our CLI, and we say, no access list 50 or what have you. So you kill the access list. And so your network for a moment doesn't have any security or what have you. And then you paste that access list back in really, really fast. And that's how you edit using the traditional access list syntax. I gotta say, I don't know why. This is like one of those things that it just doesn't make sense. Almost everybody uses this old syntax. That is not the right way to do a access list. It hasn't been probably for 15 years. We want to use the IP access list always, always, always. And it's because it allows us to edit the access list and do some other things. So that's the biggest thing about named access lists is that we can edit the lines and understand, again, that named access lists can be standard or extended. We still got that functionality. So there's really no reason to use the old syntax. Okay. Last thing, and timing is good, is what does the syntax look like? With a standard access list, our syntax is going to be, let's do the old way of doing it. It's going to be access dash list, and then I give it a number. Let's call it 1 in this case. And then I'm just going to give it an IP address. Okay, so sorry. First of all, we say whether we're permitting or denying. This is the important part, right? Permit or deny. What am I doing with this traffic that I'm about to define? Now I give it the IP address, okay? So I can be like, let's say it's 10.0 and 10.1.1.0. And then I'd give it the wildcard mask 0.0.0.255. Okay. That's a standard access list. It's comparing only the source IP address. The extended, let's make that a different color. That'll be more fun. right? Okay, the extended access list gets a little more interesting because we've got a lot more parameters to enter. So access-list, now again, that number matters. So let's say 102. And then permit or deny still. That part's still important. But this is where it drastically differs. Okay, first of all, I have to specify, remember what I said about my options, IP, ICMP, TCP, or UDP. I have to pick one of these. In most cases, we're going to pick IP. But in the event that we need to specify ports, we're going to have to go with TCP or UDP. Okay? So we can specify that. And then, boy, what comes next? Now we can start talking about source and destination. So our source comes first, and we can do the same thing where we've got a 10.1.1.0, 0.0.0.255. If we specified TCP or UDP, we could enter a port, and that would look like this. We can see this. We would say EQ for equals the number. Like, let's say it's port number 80. The interesting thing is we actually can say greater than. These are other options, greater than or less than. So we've got a lot of weird options there. We could say like, hey, this port, if it's less than 80, we're good. Again, not used too much, but it does give us that flexibility, which is nice. The other interesting thing is that we can specify a host. So let's say that the source IP address can be anybody from this subnet, but if I were to do it traditionally, I might say my server is, let's make it a 10.10.10.1. And if my server's IP address is that, and that's the only thing I care about for the destination, usually I'd have to say 0.0.0.0, which seems like a waste of time and effort, at least for me, because I'm really, really lazy when it comes to this kind of stuff. So what I can say instead is host. Really, it's not about laziness, it's about cleanliness, I think. All those wildcard masks really make your head spin sometimes. So I can say the word host. It's a key word. And by saying host, I can then say 10.10.10.1. Was that what I said? I don't even remember. I think so. So now I've replaced the need for that wildcard mask because it was all zeros anyways, so why bother? We also have another keyword, by the way, which a lot of us are familiar with, which is any. Any would basically be having 0, 0, 0, 0, 255, 255, 255, 255. If we don't care about any of the bits, we could spell it all out, or we could just call it any. And that's why a lot of us know that keyword because we say like deny any, or permit any, or something like that, permit IP any. That would allow traffic from anywhere to go to anywhere. It's effectively like you don't even have an access list at that point. But a lot of people don't know about that keyword host. So keep that in mind when you're trying to clean up your access lists. 3 minutes left. Okay, I think that's really what I wanted to. Oh, no. Wait, I almost forgot. The named access lists. Okay, so what if we're going to do a named one? What's that syntax look like? This is cool syntax. So again, we do IP space access dash list. Okay, and I will admit that I don't remember whether it's the name. I think it's the name that comes first, right? Or is it the actual is it standard or extended? Named access list. Oops. Oh, you do specify it first. Okay, according to this document. So we would say extended, because I'm going to make an extended access list, and then I give it the name. So test ACL or what have you, whatever my name is. Okay. The cool thing about this is that you hit enter at this point, and it enters into a sub prompt. Okay, before with these commands, these are just global configuration commands, and then you got to do that every time. You literally have to type access-list space 1 space before you even get to the information that you care about. All right, what kind of ports would you recommend remembering for IC&D2? Great question, Polina. I'm probably not the right person to ask that. I would, if you've got some other supplemental materials, whether that's extra CBT Nuggets videos, which I'd highly recommend, by the way, or a certification guide from Cisco Press would be a good resource for that. Certainly you're going to want to know what we'd call the well-known protocols, which is very subjective, which is why I'm maybe not the best person to ask. We'd want to know absolutely like HTTP and HTTPS. We'd want to know SMTP. We'd probably want to know SSH and Telnet. So if there are protocols that you've heard of, honestly, if they're protocols that are mentioned by the CCNA, I would memorize those. There's not a ton of them. It's not like we have 1,000 of these to memorize, or even 50. There's probably about 10 to 15 that we'd want to really memorize. I'm not exactly sure. I don't remember in mine is old, 2006. But not just CCNA, but generally speaking, as I've taken exams, there's not usually a strong expectation that I have a ton of ports memorized. There will certainly be at some point something where like they'll show you an access list and SMTP is at play, and you should probably know that SMTP is 25 or what have you. But they're not going to ask you like a curveball like, I don't know, IPsec or something like that. Like, holy smokes, I barely even know what that is. It's going to be the stuff that we deal with on a daily basis. DNS would be another one, for example. Mister, you say, what would be some of the trickiest vocabulary words to look for? Trickiest vocabulary words. Preempt, priority. I think those are probably it. Just pay attention to, go back and either rewatch this video or watch, or pay attention to as you're learning. I don't know. I mean, saying vocabulary words, I'm not exactly sure what you mean by that. CTO, hey, glad you were joining us here. I didn't know you were out there. So SSH, FTP, Telnet, DNS, HTTPS, POP3, SMTP, IMAP, SNMP. Yeah, I would not necessarily, I mean, by all means, memorize RDP, CIFS, and SMB. I wouldn't expect to see those on a Cisco exam. But any of those other ones that CTO listed out there, that would be a good one. Good chats. Throw any more questions in, or good questions rather. Throw more questions in there as we wrap up here. We'll just take a couple more minutes to talk syntax. Again, this is where I would have loved to have pulled up a router, so I do apologize again that my lab is down. But we don't have to. What I was saying there is that access list 1 permit has to start. I have to start with that every single command to enter even an access list of 5, let alone like an access list of 100 statements, right? And as we mentioned, by the way, this is something you should know from a vocab perspective. A statement is called an access control entry, or an ACE, ACE, however you want to say it. An access control entry is a statement. So Cisco might mention ACEs or ACEs on the exam. So understand that that's simply a statement within an access list, access control entry. So every access control entry has to start with that. But with a named access list, with this IP access list convention, I don't have to start it with access list. I underlined too far there. I don't have to start it with access list 1 anymore, IP access list or anything like that. I simply say permit or deny or what have you. I mean, my commands are going to be indented, and then I do all the same stuff. Everything here is the same. And again, now if you do not, the one difference, okay, is that there are sequence numbers within a named access list. Just like there are sequence numbers within a numbered access list, the difference is that a sequence number, I can now use those. Remember I said about editing? So I can actually go in there and add a sequence number. So I can specify that at the start here and look up the syntax. I'm not going to say what the syntax is because off the top of my head as I'm rushing to finish this, I don't want to mess it up. But you can actually specify a sequence number. If you don't specify a sequence number, it's simply going to add 10 to it. So like my first permit statement there, that would be a sequence number of 10, for example, and then my second one would be 20. And what it's doing is it's leaving space in there. So like what if after deploying it, it's in production, I need to add something between those two lines? Well, I could go in here and add a sequence number of 15 and then whatever my statement is. And so this is how I can go back and edit these access lists. I can also remove sequence numbers individually, so I could remove sequence number 20 or what have you. I believe there's even a command that then at some point I can actually run it and it will fix it, so to speak. So it'll make this one 20, it'll make this one 30, it kind of cascades down. That might be a Nexus thing, or maybe that's iOS too, but it's been a while. So, all right. So, Polina, thank you. You got an ACL question with POP3 in one of the training exams. I was surprised to see that. Yeah, that surprises me too, but the training exams are usually making sure that you're in good shape. So, like, don't be too alarmed by that. But, hey, you know what? They're just doing their job and alerting you to the fact that Cisco might ask for the POP3, which, ooh, man, I just Is that port 100? I think it's 100. I literally just did a nugget today on port numbers for and I believe it was 100. IMAP was 143 if I remember right. Mister, where do we apply them? Okay, that is something I did not cover very well. So good point. I guess I will toss this in as a kind of a last. I know we're a little bit over here. So for those who are able to stick around, bear with me. On a router, we have layer 3 interfaces. I like to draw these as dots for those who are new to us. And the reason I draw them as dots is because sometimes they're physical and I draw them at the edge, and sometimes they're virtual. If you have a layer 3 switch, then we have a VLAN interface, an SVI. I can draw them inside and you understand that they're a logical layer 3 interface. But either way, and the other reason is that Cisco devices, layer 3 device, they treat layer 3 interface, they treat all layer 3 interfaces the same in a lot of ways. So we need to understand that an SVI is the same as a physical layer 3 interface on a router. So any of these layer 3 interfaces can be where I apply an access list. We have this, Cisco's weird. I don't know why they did this. This one I truly don't have an answer for. We use the access class command to deploy an access list to an interface. So we're going to use that access class command, and we have to specify, is it inbound or is it outbound? So I'd use the command in or out to specify which, or within the command I would specify in or out. So if I have to, most access lists are going to be in the in direction. Generally speaking, we want to drop traffic that we need to drop as it's coming into an interface. Part of that reason is we simply, if it's coming into this interface, why would I have my router process it just to get dropped here on the outbound interface, right? So most of the time we're going to, just like it's drawn here, inbound on one layer 3 interface, inbound on another interface. But at the same time, we've got that flexibility. So that is how we apply access lists once we've created them. Great question. I totally whiffed on covering that, so thank you for asking. Standard is closest to source and extended applied closest to destination. No. Like I just said, the general rule, a security best practice is always to put your dropped traffic as close to that traffic as possible. We do not want in a network of however many routers, for example, like if I've got a host here and I'm trying to talk to a server here, why would I allow that traffic to get all the way to this router and then dropped? So it doesn't matter whether it's a standard or an access or an extended access list. The goal of standard and extended access lists are the same. They are to drop traffic that needs to be dropped. With extended, the big difference is that extended can get way more granular with the traffic that we identify that needs to be dropped. So hopefully that makes sense. That's the only difference between standard and extended, really, is the level of granularity that we can get down in there. Either way, I highly recommend that we drop that traffic as close to the source as possible. And one more question. Would there be some kind of special terminology that would be used for editing the access list? The only terminology I can think of is that sequence numbers. So be aware if we're talking about sequence numbers, or usually abbreviated SEQ. It's kind of how I wrote it out over there as I switch back here. Right, this down here, this okay, there we go. That concept. So understand that. 110. I'm not sure what that means. Oh, that's POP3. Is that what you're talking about? POP3? It was 110? Okay. Context matters, I suppose. All right. Hey, everyone. Thank you so much for coming. It's been a lot of fun to do these over the last month and a half or so. I know that we have a little ways to go for some of you to get to that ICND too. So I apologize. I know we're cutting out here while you're still going to be studying for the next 3 weeks. But I am looking forward to coming back. We're going to pick up right where we left off. So for those who can make it, look forward to seeing you in 2020. Have a Merry Christmas and a Happy New Year, Happy Holidays, whatever it is that you celebrate. And yeah, I'm excited. We're going to come back in January, and I do have some more stuff planned. I'm hoping that we'll be able to announce that here really soon. So pay attention on LinkedIn and Twitter. I'm going to be stepping up and hopefully doing a few more of these streams throughout the week. Yeah, it's going to be fun. So either way, thank you again for coming. Have a great night, and we'll see you in 2020. Take care.